Welcome to an introduction of planes in space. So planes in space are uniquely determined by a point and a normal vector. So imagine, if you will, having a tabletop, a desktop, maybe a notebook, something flat that you can imagine as a plane. So I'm going to draw myself this imaginary plane. And I need to write an equation of the plane. So I will need a point to help me fix that plane somewhere in space. And unlike lines, I can't use a direction vector, because I can imagine having an infinite number of direction vectors that could lie within that plane. So take a flat object and kind of think about that. Draw a point, or think about a point on it, and notice you could actually have an infinitely number of direction vectors that lie in that plane. So direction vector is not helpful for us in describing a plane. However, if you take that same flat surface, there is a rather unique vector, and that is the normal vector. If you orient the plane horizontally, one of those normal vectors will point upward, and the other one would point downward. But they all have the same direction, and so that normal vector creates a vector unique to the plane. So we say that planes are uniquely determined by a point and a normal vector. And note that that normal vector forms a right angle to the plane. We could think of that as being similar to perpendicular. So let's take a look at how we could use information about 3 points in a plane to write the equation of that plane. So for the time being, let's first think about what we need to find the equation of a plane. Well, we need a point, so we need an x naught, y naught, z naught that lies in the plane. Well, I've been given 3 points that lie in the plane, so I could use A or B or C. We'll make that decision in a moment. The second thing I need is a normal vector. I need a vector normal to the plane that those 3 points lie in. So let's begin by first finding that normal vector. And I'm just going to draw an arbitrary plane. I'm not going to try to graph those 3 points in space based on their coordinates. I'm going to think about this plane, and I'm going to think about the fact that it has 3 points lying in it. So arbitrarily, we'll just call those A, B, and C. This is going to help me reason through how to find that normal vector. And of course, those points do belong to their respective coordinates. So I'm going to go ahead and label those on there. So there's no ambiguity about what A, B, and C are. Now, I need a normal vector. So what would happen if I took and created vector AB and vector AC? I would now have 2 vectors that lie in the plane. And with 2 vectors that lie in the plane, I can create a normal vector using the cross product. We know that the cross product of 2 vectors is orthogonal to both vectors. So if I do the cross product here at point A, and I create this new vector AB cross vector AC, that will give me a normal vector to the plane, because that vector will be normal or orthogonal or perpendicular to both of those vectors. So the first thing I'm going to do then is to create this normal vector. So first of all, we need vector AB, and that would be 1 minus negative 2, so that's 3. 3 minus 4, that's negative 1. Negative 4 minus negative 3 is negative 1. So that's our vector AB. And now vector AC, we have negative 6 minus negative 2, so that gives us a negative 4. We've got negative 8 minus 4, so that's a negative 12. And we've got negative 3 minus negative 3, that's a 0. So if I do vector AB cross vector AC, that's going to be our normal vector. So finding that cross product, we can go ahead and create that normal vector. So having set up the cross product here with unit vectors ijk in the first row, and then vector AB in the second row, and vector AC in the third row, we can go ahead and compute the determinants. So we'll have, for our x entry, our first entry, we'll have 0 minus 1 times 0 minus negative 12 times negative 1. That becomes a negative 12. The opposite of, for the y component, we'll have 3 times 0 minus 4. It's the opposite of a negative 4. And then we'll have for our z component 3 times negative 12 minus negative 4 times negative 1. So negative 36 minus 4 will give us a negative 40. So our normal vector is going to be negative 12, positive 4, and a negative 40. So now that we have those two pieces of information, let's take a look at how we use them to create the equation of a plane. Now, to think about how we might use this information about a point and a normal vector to actually create an equation of the plane, let's go ahead and think about this given point we have, x naught, y naught, z naught. And so P is not the only point in the plane. There's infinitely many points, uncountably many. So let's just pick an arbitrary point. For argument's sake, let's call that x, or I'm sorry, Q. And that point Q is representative of any point in the plane. So we're just going to give it coordinates x, y, and z, because that could be any point in the plane. And so we could create a vector in the plane called PQ. And vector PQ would have an x component of the difference in x coordinates, so x minus x naught. PQ would have a y component of y minus y naught, and a z component of z minus z naught. And so that would be just one vector in the plane. Now we also have this normal vector, and we know that this normal vector is perpendicular or forms a right angle to the plane. So my normal vector could be represented like this. And in this case, we can say that, or arbitrarily label the coordinates A, B, and C, where A is the x component of the normal vector, B is the y component of the normal vector, and C is the z component. And we know that those two vectors are perpendicular or form a right angle. And so what do we know about the dot product of two vectors that are orthogonal, or two vectors that are at right angles? Well, we know that their dot product is 0. And so since N and PQ are orthogonal to each other or perpendicular to each other, then vector N dot product with vector PQ must equal 0. Well, we said vector N is A, B, C, and vector PQ is x minus x naught, y minus y naught, z minus z naught. So the dot product of those two vectors must be 0. So if I form that dot product, then it's A times the quantity x minus x naught plus B times the quantity y minus y naught plus C times the quantity z minus z naught. And that should all equal 0. This is often referred to as the point normal form of the plane. But now I can go ahead and write the equation of the plane that I have here that contains points A, B, and C. And so for the point in the plane, let's go ahead and simply use A. So we're going to use the point in the plane as -2, 4, -3. So now, writing the equation of this particular plane, A is the first component of the normal vector, so I have -12 times x minus the x coordinate of my point, which is -2, plus B is the second component of our normal vector, or the y component, that's a 4, times y minus the y component of my point, that is also 4, plus, now the third component of my normal vector, or the z component, is -40. So I'm going to write that as -40 times z minus the z component, or z part of coordinate of my point, which is -3. And that must equal 0. Now, you could go ahead and use the distributive property and write this in a more succinct form, but leaving it in this form as -12 plus x, or -12 times x plus 2, and plus 4 times y minus 4, minus 40 times z plus 3 is perfectly fine. I hope you find this helpful.